So this new module is on intersection and traffic signals. So we're going to primarily focus on traffic signals in this. We'll obviously get to roundabout right after this, but like next couple of weeks we'll focus on traffic signal design, and then we'll talk about roundabouts and how they might be better than traffic signals, and then we'll move on to the capacity analysis for both roadway sections and freeways, specifically freeway weaving segments, and then level of service analysis for intersections. So that'll be sort of the plan for the remaining 2 modules of the class, looking at intersections today, and then looking at the level of service analysis for intersections and roadway segments both. Okay, so this is about at-grade intersections. So we're not talking interchanges, talking at-grade intersections. So your 4-legged, 3-legged ones where the roads meet at an angle. Maybe it could be a 90-degree angle, and that's ideally what we want, like roads intersecting at 90 degrees, but that doesn't always happen. There are all sorts of oblique angles sometimes the road will meet at, but that's what we're talking about. And those are very complex because of conflicts. And conflicts is, at any point on the road, there could always be sort of rear-end conflict, right? If there is a speed differential between multiple vehicles, there could be a rear-end conflict. However, often you end up on intersections, you end up with more severe conflicts. There are sort of crossing conflicts. And crossing conflicts are when the traffic streams are at an angle with each other. They're not parallel to each other, but they're at an angle with each other. And if that happens, those crossing conflicts could be more severe in nature, could be more deadly. There is obviously, on an intersection, there is also the merging conflicts. So when we talk about merging conflicts, we're talking about these right turn type conflicts. So when you have an intersection like this, I'm just going to quickly draw it out here. A merging conflict looks like the conflict between the vehicle that's going this way and the vehicle that's turning right from here. So this is a merging conflict, example of a merging conflict. And typically we know merging conflicts are going to be less severe. They're not going to be fatal they're less likely to be fatal and cause a lot of injury. So that's one reason why roundabouts are safer than your traditional 4-legged intersection, because on roundabouts, you'll end up with most of these conflicts are going to be at this type rather than this crossing kind, where you have one stream of traffic, so directly intersecting at a right angle, leading to a T-bone type crash. So what we do is, like, to manage these conflicts, we have this level of control, which can be categorized into 3 levels. One is basic rules of the road. So sometimes you will see intersections with no traffic controls. You would come across those, not always, but you might come across in neighborhood streets, for example. And there, you have the basic rules of the road, where the drivers on the left will yield to the drivers on the right. And then there is direct assignment of right-of-way. So that's your yield sign or your stop sign. So that's another level of traffic control. You're directly assigning right-of-way. When you come to an intersection, if you have the stop sign, then the other person has the right-of-way. Or if it's a 4-way stop, whoever comes first has the right-of-way. So those are your direct assignment of right-of-way. And then level 3 is basically what you have is the highest level of traffic control, which is the traffic signal. So in basic rules of the road, right-of-way is not assigned. Driver on the left yields to a driver on the right. And then through vehicles have the right-of-way over turning vehicles. And then you see these types of situations sometimes when you have one person sort of a left turn into a driveway, and then they have to, that's kind of an intersection, but there is no stop sign or yield sign or anything for the left turning folks, and they're just automatically supposed to yield to the people who are going through. So that's your basic rules of the road. And then one of those rules is through vehicles have the right of way over the turning vehicle. So this is something that becomes important, and we'll do some problems based on this in a little bit once we've covered this chapter, is this limitation of sight distance at intersection by buildings or other obstructions. So that creates a line of sight issue. And this is something that it's a related concept to this, is the concept of daylighting the intersection. Okay? That means you're eliminating any potential hindrances that might block the view of the driver from watching either the pedestrians, watching the bicyclist, or watching other cars from approaching. Because sometimes what happens is that sight triangle might not be clear at an intersection. So for example, if you look at an intersection like this, I'm just going to quickly draw this out. So at an intersection, sometimes if you have a car approaching from this direction, you have a car approaching from this direction right here, you have a car coming from here, they need to be able to see what's going on around them over, like, so if there is a traffic approaching from this direction from here, and then there is a, let's say if there's or let's think about the traffic that's approaching from this direction right here. So if you think about the traffic approaching from this direction, they need to be able to see without any obstruction what's going on over here, and they need to be able to see who's coming from here. If there is a building, or if there is a car parked here or here, for example, if there's a car parked over here, that would cause a problem for the drivers to be able to see who's coming through. And that could be potentially deadly for bicyclists and pedestrians as well. So what we want to do is we want to make sure that the sight triangle is clear. And then especially if you have some kind of a rules of the road situation, you always want to make sure that there is no obstruction that's blocking the view of the drivers. And I think there are some calculations involved with respect to, that the line of sight has to be perfectly clear. So how far can this obstruction be over here, so that the driver approaching from this direction can see the traffic coming in from here? Okay? So that's something that we're going to work on. But sight triangles are very, very important. They're important pretty much everywhere, but they're very important if you have sort of a rules of the road type, no control intersection. And sight triangle is the triangle created by line of sight of the drivers in the vehicle's path to the point of conflict. So point of conflict, this is another sort of concept that you should be aware of. So for example, if the traffic is moving this way, if the traffic is moving this way, and then there is traffic moving this way, this point right here is the point of conflict. And this is right here is the point of conflict. Yeah. So you have to be aware of what we mean by point of conflict. So what we do is, when we are drawing the line of sight, let's say the car is approached over here, they need to be able to see the driver here. So this becomes their line of sight. And we want to make sure that there is no building that encroaches ahead of this point. Because if there is any building encroaching ahead of this point, if there is any building approaching all the way up to here, the driver here won't be able to see the person over here. And then there would not be enough distance available to stop when they do finally see it, because this vehicle would have to approach even further up, and that would be causing problems. So level 2 control is your two-way stop, yield control, multi-way stop control. All-way stop control are typically not something that we want to do. We want to implement. They are there, right? In some shopping centers, they are there, but they can be very confusing. Who came first? How does the pedestrians get yielded to? Could be very confusing. But in some ways, they are useful, because everybody is at least expected to come to a full stop, or at least a rolling stop, right, in California. But multi-way stop control is also sort of a level 2 control. There is no traffic signal, and then there are, we talked about the warrants for traffic signals when we were talking about traffic studies. There are actually warrants for stop controls as well. They're not as detailed, and if you can interpret and read signal warrants, you can read and interpret stop sign warrants as well. That's not an issue at all. I'm not worried about it. But those are also have some conditions governing them. So putting a stop sign, when can you put a stop sign versus not? Again, there are stop sign warrants and there are multi-way stop control warrants. So there are warrants for all of these different levels of traffic control. So we'll talk about traffic signal control, obviously mother of all traffic controls. And the idea is that the assignment of right of way is going to be complete. The drivers won't have to, apply any judgment at that point. But that's not fully true, right? Because you would have permitted left turns. So when I say almost no judgment, I'm also talking about at least in the case of protected left turn. At least in the case of protected left turn, no judgment would be required. But then again, if you have permitted left turn, so that's your green ball rather than green arrow. So do you know what mechanism are we using now? We are trying to move away from that green yellow ball for the permitted left turn. You know what mechanism are we using? Anybody? Yeah, back there, Max. Yeah, it's a flashing yellow arrow, FYA, flashing yellow arrow. That's basically your permitted left turn. Yes.
For protect permitted, is it just the doghouse light?
Doghouse light?
The 5 light array?
Yeah. So so sometimes some signals have both protected left turn phases and then they allow some permitted left turn as well, right? So there you need sort of both of those things, right? So you need to be able to show a green arrow, but then if there's a flashing yellow arrow, you might be able to denote that. Although right now, I don't think a lot of communities have implemented flashing yellow arrow with a protected green arrow turn. So that's also, it's sort of a work in progress, the flashing arrow implementation, but it's really been found to be way safer than the green ball indicator. That's basically your that's basically what's used here. And as I said, warrants for signals are very detailed. And then when you get to the signal control, there is pre-timed and actuated control. We talked about that a little bit. And in actuated control, we have semi-actuated, fully actuated. And then there is this volume density control, and sometimes it's called adaptive signals that are completely reliant on not detecting individual vehicles, but sort of looking at what's happening overall at the intersection approach, what type of volume is approaching, what type of congestion is happening on each of these lanes. So those are sort of your more advanced type of signals that are called volume density control. And they also have sort of great detection capabilities, but they're detecting not like group detectors. In the case of semi-actuated and fully actuated control signals, they're trying to detect the presence of individual vehicle over the detector or on the camera. But in volume density control, those signals are looking at sort of multiple vehicles, what's happening with the volume, what's the rate of the volume coming in on the approach, and what's the density, how much congestion there is, so that they can anticipate what's going to be the demand at the intersection in the very near future. And then, so those are sort of the advanced type of signals. Again, the point of all of these is to become more demand responsive, right? And obviously demand responsive signals like actuated and fully actuated and even volume density, they have value in terms of operations, right? Because they can really minimize the delay compared to a pre-time signals. Still, you might have noticed that when there is construction on the road, sometimes they would convert that signal into a pre-time signal. And that can be pretty frustrating because that means if they have construction going on and the detectors, for example, are not working because they've dug up the road or whatever, and there is something wrong with the detectors, sometimes the detectors go bad, or sometimes their camera system doesn't work. Whatever is the reason, we switch over to pre-timed operation, and that can be pretty frustrating because you're saying there is no demand that's competing with you, but you still have to stop. And if that starts to happen quite a bit, it's obviously operationally bad because people are having to stop for no reason. But then it's also bad from a safety perspective because people see that happening more and more, they just start running red lights. They said, to heck with that. I'm not even going to bother with this stuff, right? So that's a problem. So that's why we've pretty much moved away from pre-time signal design only We do pre-timing of signals, but either because of construction or when we can make sure when there is demand coming in from all sides, so no side is completely uncongested. So every side is just fully congested, and then every signal cycle is just max out. We'll talk about what maxing out is, but the idea is that it just runs its course. You can only give it that much green to that approach, and it has taken that green time. So that's like on a fully congested situation or on a coordinated signal cycle basis is where we have pre-time. But other than that, we run actuated signal control because they're both good for safety as well as for operations. So let's now talk about sort of actual signal timing now, right? So today's lecture will probably get to the point of where we are dealing with sort of your yellow and all red intervals, because those are important from a safety perspective as well. But signal phasing, it's important because signal phasing is the sequence of individual phases. Okay, so signal phasing, right? Signal phasing is sequence of individual signal phases or combination of phases within a cycle that define the order. Okay, so when we say individual phases or combination of phases, there could be, there could be multiple phases. So for example, there could be like a sort of a permitted protected phase, right? So that is also like sometimes thought of as a single phase. So it's a sequence of either single phases or combination of phases within a cycle that define the order in which various pedestrian and vehicle movements are assigned the right of way. So as you get the green, so then we say that phase is active. The phase that has the green sign, green signal, that phase is active right now. Okay? So there could be multiple movements that are going at that time, through and green. So it could be like a through and green phase that's going, or it could be just the left turn is going in one direction, or whatever it is. But phasing is sequence of individual phases to determine the order in which pedestrian and vehicle movements are assigned who's going to go. So that's your right of way. A cycle is complete rotation through all of the indicators provided, green, amber, red, and all red, for all approaches involved in that signal. So basically, it's the, once the light turns red on a signal, and then that light turns green again, that basically completes the full cycle. So when you think about the cycle, this diagram is sort of the key here. Okay. So you could say this is a 60-second cycle, 35 seconds, the major street is green, and then there's a full second of yellow interval, 1 second of all red interval, and then the other light turns green. Okay. So today's lecture, we'll definitely want to learn about how do we determine how much time we want to keep it green. How much time we want to keep it yellow, and how much time we want to keep it all red. Okay. And this all red is sort of your safety mechanism, so that if somebody's already entered the intersection on yellow, they can safely exit the intersection at that speed. Okay. So that's your all red interval. So you don't begin the other phase until there is some clearance time associated with the previous phase. So if somebody entered, you want to be able to let them go. And then there is, like, obviously, sometimes phases are also called intervals, or like, a subset of phases is also called intervals. So within a phase, there could be LPI, for example, leading pedestrian interval, right? So there might be that. So there could be, obviously northbound green phase or northbound left or all that. So all of that could go into a cycle. But right now here on this figure, I'm showing you a very simple two signal cycle. Two phase cycle. There is one, it's basically, these are your intersection where there is no exclusive left turn phase. It's just, you're supposed to yield to the left turners. I mean, you're supposed to yield to the through vehicles if you're a left turner, and that's it. On north, south, east, west, there is just one green light. So that's why it's a very simple two-phase signal. Now, there is some, by looking at this figure, you should be able to tell me what is the advantage of having as few phases as possible. Why would you not want to have, so right now this signal shows 2 phases. What do you think will happen if you had 3 phases or 4? Thoughts? Anybody else? What's that? Yeah, so you're cutting the pie into smaller pieces is right, because every time you have a phase, you're going to have to provide an all red interval and a yellow interval. And then on top of that, when the vehicles come to a stop and they start moving again, right, there is some time lost in that. You know, maybe somebody's looking at their phone, and even if they're not, if they're coming from, think about this. If the vehicles keep moving, versus the vehicles have to stop for red light and then, you know, go ahead after that. So it takes some time to accelerate, stop, decelerate, stop, accelerate, and then get to their original speed. Yes, please.
Is this like what they call like the difference from the free flow speed that you use for timing LOS?
Yeah, so difference from not quite the free flow speed, but yeah, so when you're doing the level of service analysis, there would be a delay component. And then we want to measure what that delay is. So if the delay is based on, we measure the approach delay, right? So that approach delay is basically, what if you just got a green and you kept going versus what was your actual time passing through that intersection, right? So that's how we determine the approach delay. And then those concepts are very related. But those approach delays, the concept that we are dealing with here is going to be more like a sort of startup loss time. The startup, that time that you lose when you are going from a stop to your desired speed through an intersection. And then there would be a clearance loss time. And the time that's lost, because a lot of people are not going to use this all red interval, they're going to actually stop, which is great, which is what we want them to do. But there is a time loss associated with that. So that's why, from an operational perspective, and from potentially even from a rear end collision perspective, you want to have as few phases as possible. But there is a conflict here, right? The conflict is with safety. Because if you're not assigning right of way, if you're almost forcing the left turners to always yield to the through vehicles, you are basically allowing some conflicting movements to go at the same time, right? So that's what's happening right there. So that's sort of a problem. And that's why, even though you want to minimize phases from an operational perspective, from a safety perspective, you know, if you can assign the right of way to the extent possible, that's a good thing. So that's your conflict right here. And that's why, you know, signals could be very challenging from a safety point of view if your mindset is to move cars as fast as you can. Because then you'll try to minimize the phasing, you'll allow right turn on red, you will probably not worry about approach speed, you'll have the approach speed faster, because if, as you will see, if you have the approach speed to be fast, then you could have smaller all red interval, right? All of those things are great from an operational perspective, but they might be terrible from a safety perspective. And that's the dilemma, that's the challenge. I think we should probably favor safety. We should, but it doesn't always happen. And the delays, you know, the drivers are pretty frustrated about delays, and that's the problem right there. Yes.
I'm just curious, like, is there like a point where it would just be easier just to consider like a flyover ramp for a certain movement?
Yeah, but those are very, very expensive. So yeah, so the question is, at what point do we give up on the signal and start thinking about, okay, maybe we just sort of need to just grade separated intersection, just design an interchange or ramp. You know, typically you won't see that unless it's a uninterrupted flow facility itself, like unless you have like a 101, highway 1 type thing. You know, even on highway 1, you will see some traffic signals. You know, so yeah, I mean, there is that benefit cost analysis that has to be done then, right? So you have to think about, but before you get to that point, because creating an interchange is such an expensive cost, a high cost project, that we try to minimize that to the extent possible, right? So I mean, yeah, so that would be a good idea to kind of think about, you know, grade separating the intersections, and we do have to do that a lot of times, but that's not always the ideal situation. because it's so expensive. Signal phasing terms and definitions, cycle length, time in second that it takes a signal to complete one full cycle of indication. Usual values between 40 and 180 seconds and measured in 5 seconds term. Now, 180 seconds is heck of a long signal, right? I mean, if you miss one green light, you're standing there for 3 minutes. That's a long time to wait for any location. Yeah, so I think that 180 signal. So a pretty long signal cycle can be okay. So there is a point where increasing the signal time increases the capacity of the signal. But if you're dealing with like 180-second cycle, that's too much. I mean, there are some signals that have that kind of a cycle, but it's too high. Yes.
Isn't there also like the practical limit with consideration of pets where you don't want to go above 60 to 90 seconds because that just causes frustration and encourages jaywalking?
Definitely, yeah. So it's even more frustrating in the sense that, you know, pedestrians have, even though they are at risk, but they have the most sort of, how should I say, they're most susceptible to actually running the signal or what you call jaywalking, like, you know, try to kind of cross the signal at wherever they want to cross. So yeah, I mean, 3 minutes is way too long. 2 minutes is pretty long. And yeah, you're right. Like, you know, I mean, I've seen signals that have like 140 second signal cycle. And then you might be wondering, what's the concept of signal cycle? What do we even mean by signal cycle if we have actuated control, right? If you have actuated control where you're being demand responsive and you're trying to address the demand from each direction. But think about situations during peak hours when there is demand coming in from every side and every signal is just getting out to their maximum point. Every cycle, every phase is getting their maximal allocated time. So if you sum up all the maximum green time on a traffic signal, that gives you your sort of your cycle time. So you're dealing with that at that point. And yeah, 180 seconds is a bit much. Typically 5 seconds rounding. I think 140, more than 140 seconds are fairly rare. Let me put it that way. You would find 140 seconds some places, but you know, that's pretty long still. Yes. Highland Santa Rosa. I don't know what the maximum time there is. Yeah, that's a good point. 3 minutes? 3 minutes. You know, sometimes when we are waiting, the wait can feel longer than it really is. So I would be surprised if it's actually 3 minutes. But in some cases, it might extend that long if there is a train coming and then they put that signal red. So it could exceed in special circumstances to that level if they have to keep that, wait for the train. But I doubt in normal circumstances that goes to as high as 3 minutes. That seems high to me. Right? Probably a little bit lower, maybe 2 minutes, maybe 140 seconds, but 3 minutes. Yeah, I don't know precisely what that time interval is, but maybe I can find out. So I'll see if I remember, find out, I'll try to find out. Okay. Interval is period during which no signal indication changes. So yellow interval is the change interval. So basically the interval where nothing changes in the cycle, that's your interval. It could be yellow interval, green interval for a certain approach, the red interval for that approach, and then all red interval when all approaches are red, right? So that we require for safety to safely clear out the intersection. A phase includes the green interval at the change and all red interval. So a phase would include the green time for that phase, yellow time for that phase, and all red time for that phase. And all red time is also called clearance interval. So a phase is a sum of 3 different indication times: yellow, green, and all red, right? Saturation flow rate, maximum number of vehicles observed per unit time of green, right? So per unit time means per hour of green. So the unit for saturation flow rate is vehicles per hour of green per lane. Okay, that's your saturation flow rate. On a typical intersection lane, if it's a flat, your typical urban intersection with not a lot of, these, like, the speeds that we have in our urban areas, unfortunately, 40, 45 miles an hour, you're talking about like maybe 1800. That's pretty high number, but that you can achieve that. Yes.
For NCHRP uses 1700.
1700 is probably right, but I think they use a little bit lower value. You could get, yeah, because they're probably assuming a little bit lower approach speed.
Down to 1400 if you start doing heavy vehicles.
Right. And then, yeah, and it could change if you have like right turn, a lot of right turners, for example, within that approach. So those numbers could go down. But typically, yeah, 1900 is probably like just sort of is the highest limit that you would see. NCHRP, as was mentioned, uses around 1700, which is reasonable. Again, you could probably get this up if you raise the speed, right? If the approach speed is high, you could probably move more vehicles per hour of green, but you probably don't want that, at least not in all cases. Critical lane, it's a lane or lane group that consists of maximum number of vehicles in a phase, right? So this concept is important to learn because the idea of critical lane is when you move vehicles in a phase, or vehicles or pedestrians, whatever it is, when you have movement through a traffic intersection on a signal phase, you would be able to allow more than one movement because there is no conflict between those movements. What I mean by that is, if you have eastbound traffic going on an intersection, you can allow the westbound traffic to take the same time, to use the intersection at the same time, because eastbound and westbound traffic has no conflict within each other, between each other. So I should say eastbound through movement and westbound through movement. The traffic that's going through the intersection straight through, they have no conflict. So you can allow both of those movements to go through. But when you're talking about critical lane or lane group, whether you're going to base your design on eastbound traffic or the westbound traffic depends on whichever one is higher. Okay, so going on that certain phase, your critical lane group is the maximum number of demand that is faced. Now, here you have to be, this is all expressing that in the terms of vehicles, but it could also be pedestrian. That's your critical phase. It's a critical lane group, could be either vehicular movement, but they could also potentially be pedestrian movement. And if there is sort of a pedestrian type of demand, where your all approaches all the time, pedestrian is the sort of your critical lane group, then at that point, you might want to consider something called, a scramble, ped scramble, where you allow pedestrians to cross in any which way that they want, right? Even they can cross diagonal, and you could have exclusive pedestrian phases in that scenario. I mean, you might still allow pedestrian to cross over in a non-conflicting movement, but you could also do what we call, what ped scramble or Barnes dance or whatever. There are some fun terms there that we use sometimes. But if your pedestrian phase is always becoming critical from all approaches, then you might want to consider those types of things. But here I want to point out even though the definition here says maximum number of vehicles in phase, basically whatever is going to need maximum time to clear. And those could, in some cases, be pedestrians as well. So your critical lane group, when you're assigning the green time, what are you going to base your timing on? It's the critical lane group is what you're going to base it on. So if your eastbound has higher demand, then you're going to base your timing on eastbound traffic. If westbound has higher demand, then that becomes your critical lane group. So signal phasing is observed during peak hour, right? So basically we want to observe. So for capacity of the signal and timing of the signal, it's very important that we make an estimate of what we call the saturation flow rate. Okay, saturation of flow rate happens during peak hour, right? So we need pretty good amount of traffic. And then saturation flow rate is the flow rate at which, if there is a steady stream of demand, right? If there is pretty heavy demand and you had continuous green on a signal, at what rate would you be able to discharge the vehicle? That's your saturation flow rate. So you require saturated flow conditions to be able to observe that for the most part. Maximum number of vehicles per unit of time per green cycle, observe the full stream of vehicles passing through the green. A full stream of vehicles, if they kept coming in and coming in and coming in, how many vehicles would you be able to pass through in and out? Now the question is, what happens if you have a signal where you have, there is demand, but it's not saturation demand, right? How would you estimate saturation flow rate in that scenario? Yeah, do you want to say something?
I was gonna say just estimate it based off the traffic volumes, percent trucks, and and how many right turning vehicles there are, and just use the NCO and just use the HCM equation.
Right, there is an HCM equation for it. So there is that. There are two ways of doing that work, right? So if you don't have sort of fully saturated conditions all the time, but you still want to estimate capacity of that intersection because you might have that intersection serving as sporting events, maybe a Taylor Swift concert, right? So in those days, there could be pretty heavy demand. And then if that happens on that intersection, but you don't have these conditions normally occurring. And if that happens, you still want to be able to observe or at least estimate what is the saturation flow rate. So there are two ways of doing that. One way is there is highway capacity manual that says, your ideal condition capacity is 1800, 1900, whatever it's at NCHRP says, right? That number, and then you make an adjustment for how many heavy vehicles, how many right turning vehicles, what's the lane width, what's the grade. So there is an adjustment factor for all of those things, right? So factors of adjustment, you just keep multiplying those and keep lowering that flow rate, saturation flow rate. So you take an ideal flow rate and adjust that ideal flow rate for your field conditions. Okay, that's one way of doing that. But there is actually another way of doing that, and that's basically by collecting data, maybe not on fully saturated conditions, but even on mildly sort of saturated conditions. Okay, and that work is done using. Let me go back to an empty sheet here. So let me show you how we can do that. So let's see if I can draw some boxes. So let's say this is an intersection approach, right? You're approaching an intersection, and let's say this is the intersection right here. And I have my stoplight over here. And my stop line is right here. And now I have cars that are stopped here. And obviously I don't have fully saturated condition in that once I turn green, these cars will flow through and empty out. So I don't actually have to wait for fully saturated, absolutely congested conditions to develop. I might be able to estimate my saturation flow rate anytime I have maybe 4 to, not quite 4, but at least if I have 8 vehicles lining up and a red light, then I can estimate the saturation flow rate for that approach. And we used to do a lab on that, and you might still do that lab in this year's class. But that approach is, that way we can still estimate the saturation flow rate. How do we do that? We do that by looking at, on the red cycle, or when the signal is red, there will be a queue of vehicles, and we need the queue to be at least 4 vehicles. The longer is better, but at least 4, I should say at least 5 vehicles. At least 5 vehicles have to be there in the queue for us to be able to do this estimation of saturation flow rate. And the way we do that is that we start noting, we stand here at this location, we stand here on the side of the road, and we, using a stopwatch, when the light turns green, we start observing the time as each of these individual vehicles passes the stop line. And we have to be consistent. If you're talking about front bumper, then we base it off a front bumper. We're talking about rear bumper, then we base it off the rear bumper. Whatever it is, whenever the front bumper of each vehicle passes the stop line, we note the time. Okay? The first vehicle passes, the second vehicle passes, the third, the fourth, the fifth, all of that happens. So what we do is, we end up with a graph like this. Let me draw that up. Go ahead.
Is what they call the critical headway?
We do talk about critical headway. We talk about saturation headway is what we are estimating. Critical headway would be something different. Is that critical headway is typically used when we're talking about what type of gap or headway people will accept versus reject, right? That's on merging conflicts typically. And that could be on two-way stop control intersection, even on right turn on red. That's what your critical headway is. This one is what we're talking about is saturation headway. So what would happen is typically you'll end up with a graph like this. You'll end up with a graph like this. So I'm going to just draw this out. Freehand. This one, draw a little line. But it's just simple drawing. So you'll end up with a graph something like that, looks something like this. So what will happen is that the gap between the first and the second vehicle, this is your first headway. So this is, here you'll have number of headway on the x-axis. Okay. And then this is in second, time in seconds. Right. And then that time in seconds will be pretty high between, so your first headway, if you're talking about first headway, that time would be very large. Or you can even think of it as a 0th headway, right? So number of headway is 0. This is the time between when the light turns green and the first person crosses the road. Or first person crosses this stop line right here. So when the light turns green and the first person crosses this stop line, that's going to be the time. So this is sort of your 0th headway. Your first headway would be the difference between when this person passes the line versus when this person passes the line, that time difference. That second headway would be a little bit smaller. The third headway would be even smaller. The fourth headway would be even smaller because now these subsequent vehicles have had some time to react to the green light. They're ready to go. And as their time comes, this gap keeps reducing, this headway keeps reducing and reducing. And after fourth or fifth headway, this becomes sort of a constant line of vehicles. So this is what we call, once you have established that saturation, this becomes your saturation headway. So if you have more, that's great. But headways after the fourth or fifth headway becomes constant, and that's what we call the saturation headway. So this time interval, if you draw a line from here, this time interval is called the saturation headway. So once you know the saturation headway, you can convert that into saturation flow rate, right? Saturation headways can be converted into saturation flow rate. We did talk about that in our lecture, very first lecture at the very beginning. Does anybody recall how do we convert saturation headway into saturation flow rate? Do we recall? Saturation headway is the gap between consecutive vehicles is your headway, not gap, but the time difference when passing a certain point is the saturation headway. So saturation flow rate is number of vehicles in 3,600 seconds. That's 1 hour. It's 3,600 divided by the saturation headway. So once you know the saturation headway, your saturation flow rate is easy to get, equal to 3,600 divided by saturation headway. That makes sense? So you don't require like, a ton of cars fully congested to be able to actually observe what your saturation headway is going to be. So you could do that with no saturation condition. I mean, you'll require some sort of saturation, but not full saturation. You only need like maybe just 5 vehicles line up in the queue on a red light, and then departure pattern will give you. But if you add up this time right here, that's your lost time every cycle, which keeps going down as you have more vehicles stopped up. Per vehicle, that stop time goes down. But there is some stop time that will happen every time light turns from red to green, right? So that's what we call, if you add up these times, these are called startup lost time. We add up all these times here that you're losing, over and above the saturation flow rate. So for startup loss time, the only thing we're considering is right here. So we're adding the time from here to here, time from here to here, time from here to here, and time like whatever this little thing is, right? If there is anything like that over there, then that time as well. So you add up those times and those are your startup loss time. Okay, so we can estimate saturation flow rate even from a field study. And there would be an example of this as well. So we'll work that out. But that's your saturation flow rate. So let's go next here. Okay, so let's clear this out. Okay, so lost time is the wasted time during no one is getting into the intersection. Nobody can move. It's big determinant of capacity and delay. Occurs twice at each phase. So as you add phases, you're losing time twice. One is at the startup, one is at the end. At the beginning of the phase L1, usually about 2 seconds are lost at the startup time. And then at the end of the phase, about 1 to 3 seconds are lost. So that's another sort of lost time. A lost time per cycle is about, like, if you have anywhere between 2 to 4 phases, you could end up losing from anywhere between 6 to 20 seconds every cycle that you're going to run. You're going to lose that much time. Now you could say, okay, if I'm talking about hourly, I can minimize my lost time by minimizing my number of cycles. But again, that's bad because then you're getting into pretty long cycles, right? So that's not always ideal either. So more phases obviously will lead to more delay, and then you can't keep making the cycle longer to avoid those delays. That there are no free lunches there to be had either. So, but again, from a safety perspective, you still might need more phases. So then you have what we call the effective green. Okay, effective green time. That's the green time available for vehicles to be able to move. It's the small g is the effective green time. It's the green time at which vehicles can move at their saturation flow rate. Potentially, they could move at their saturation flow rate. Where G is the effective green time, small g, capital G is the duration of green signal. So what we do is we assume that people are going to use that yellow and all red time to move, and they do. So we add up G plus Y plus all red, and you subtract from that the lost time, startup lost time, and the clearance lost time. Okay, so capital L is the duration of total lost time. So it's capital G is the duration, and then you add up yellow and all red, and then you add up the lost time. And lost time estimates, you'll have to either make an estimate or it will be given to you in the problem. Then now, how do we time? So when we are timing a signal, this is very important from a safety perspective. How much yellow and all red time we want to provide. Yellow and all red time combined is called the clearance interval, not to be confused with clearance loss time. No, that's not clearance loss time. It's clearance interval. It's the interval that we are providing. So when you're thinking about it conceptually, loss time is something that happens in based on how people react to a certain situation. This is like sort of an outcome. But interval is something that a signal timing designer would actually build into the traffic signal controller. Okay, so clearance interval is something that we will provide at an intersection approach. It's the yellow and all red. The yellow time is T plus 1.47 times S85 divided by 2A plus 64.4, 0.01 capital G, where G is the grade, and all red time is width of the road that needs to be crossed. L is the car length, 1.47 S15. Now, my question to you is, what's the, okay, yeah, let me, A is the acceleration or the deceleration rate that a vehicle could generate. Okay, so A is the deceleration rate that you could potentially have typically in the range of 11 to 12. You could go lower at 10, right? Just to kind of be on the safer side. You provide a smaller number here. Yeah, if you divide by a smaller number, makes this quantity larger, makes the yellow interval larger, makes it safer, right? Yes.
Isn't that actual use 11.2?
11.2 is for most situations, but for determining yellow time, they might actually recommend a lower number of 10 seconds. Just to be on the safer side. But you're right, when you're determining stopping sight distances on basic roadway segments, then yeah, you do use 11.2 feet per second squared. Okay. Now, quick question here in the formula. What should be the unit of S85 and S15? So 85th or 15th percentile speed is what that's denoting. But what should that unit be? Feet per second? It's miles per hour. Okay. And why? Because I have the 1.47 factor that I built into it. So that means I have a higher speed limit available to me. I'm sorry. The conversion factor is already available to me. So 1.47 takes care of that conversion between miles per hour to feet per second. So now that's why I can use the time interval t in seconds. Y could be in seconds, but the speed can be input into miles per hour. Oops, what happened? So that 1.47 factor allows me to then use that miles per hour, speeds. Now, one thing here, when you're talking about yellow interval, I'm using fast moving vehicles because again, I want to be conservative side. So I'm moving 85th percentile speed, right? So I want to be able to make sure that the 85th percentile speed have enough, time available for them to not get, stuck in no man's land. And if they want to pass through, they can pass through. If they want to stop, then they can stop on yellow light. So that's your yellow interval. But now on the all red side of interval, I'm using 15th percentile speed. Because again, I want to maximize that time, clearance time. So I'm assuming that once the vehicle's entered, maybe they will enter slowly. Or maybe they won't be able to clear out the intersection as fast as possible. So again, to be on the conservative side, I use a lower speed, which is a 15th percentile speed. So if you use this type of an all red interval, only if one of those 15% of the vehicles comes in at the end of the cycle, that's when they can potentially get stuck. Right? But they will be fine because then on the other side, you have some startup loss time for the new approach that's going to start their movement. So they don't, so there is, I think these formulas are fairly conservative, which is a good thing. So that's why we use 15th percentile for the all red interval and for 85th percentile for the yellow interval. Yes.
For the all red interval, we not take into account the startup loss time and the time it'll take for them to actually reach the conflict point.
So we don't worry about startup loss time. Loss time is something else. It's an output of the behavior that the road user would have. So that's not something that we are considering here to determine the yellow and orange interval. We're just considering if they need to be able to brake, would they be able to brake it at an appropriate distance? Or, and for the all red, if they decide to continue going, would they be able to clear all the way across on the other side? And there are two important considerations. There are two formulas here. And those formulas are, one is based on the width of street being crossed. So if it's a mostly vehicular intersection, then you base your all red time based on vehicular traffic. But then if you have pedestrian crosswalk on that signal, then you have to consider that as your crosswalk. So this is what that looks like the difference between when you're trying to determine the all red interval. It's determined either based on W. So it's the distance from the stoplight on this approach to basically be able to clear out the conflicting area of the intersection. So W is used, this W formula is used where you don't have pedestrian crosswalk or you don't expect a lot of pedestrians. But if there are pedestrians, then you make it even more conservative. You want to make sure that they can, before the light turns green for these pedestrians right here, before the light turns green for these pedestrians over here to cross here, the car who did not stop at red interval can pass through here. So that's why you include this W as your all red estimate. That makes sense? Questions? Right. So you could use either of those formula depending on the context, but you could see that the P value will give you a more conservative estimate of the all red, means a larger estimate of the all red. And again, in this one, you want to be careful because I put small v. If you apply this formula, then basically your speed has to be in feet per second. Okay, this formula right here, that means speed is in feet per second. But if you apply the formula that's here, because I have that 1.47 factor, that means I can put S15 as miles per hour. Okay. Now, how do you actually estimate these 15th percentile and 85th percentile speeds? Right? How do we actually get that? You can get it from the field by doing a spot speed study on the approach. But if you don't want to do that, there is a rule of thumb is that for 85th percentile, add 5 miles per hour to speed limit. And then for 15th, subtract 5 miles per hour from speed limit. That's usually, so 15 to 85th is your 10 miles per hour pace, which is reasonable. Yes.
So don't I prefer to add 7 now for 85th percentile? Or
I have only seen mostly like 5, but again, 7. If your speed limit is more than 7 miles per hour than the 85th percentile, I think something's got to give there. Like, you know, because now you're saying,
or I think that might just be used for is as they call the design.
So the design speed might be 7 miles per hour higher than the speed limit. That's possible. But again, this is like interrupted flow you're talking about, right? So think about the context here. If you have traffic signals on an approach, that means you have interrupted flow situation. And that means you're not talking about a freeway, right? Freeway won't have red light or anything like that, right? So this is interrupted flow situation where the speeds are lower and going above 5 miles per hour is fairly reasonable question. So that's sort of a rule of thumb that you could use. For S85, you can add 5 miles per hour to the speed limit. For S15, you can subtract it. And again, that makes yellow interval to be larger and an all red interval to be larger as well if you apply these formulas and not directly the speed limit, which I think is reasonable because you want to be more conservative when you provide these. Obviously, if you have an all red interval and yellow interval, you know, that means nobody would move for some times, and that could happen, but that's okay because that might be reasonable given the safety considerations. Okay, we got this. Again, if you're applying this formula, remember no factor. So pay attention to the unit. V is in FPS, not MPH. So no 1.47 factor here. So that means in this formula, at least you have to put V in feet per second. Okay? If you decide to apply this formula. And again, the value of P will give you more conservative estimate of that all red interval. So use that to the extent possible as well. So this clearance interval, the range of yellow interval 2.5 to 6 seconds, rounded up to nearest 1/10 of a second. And then range of all red interval is between 1 to 3 seconds. That's typical value that you would find in most places. Now, this is what happens from if you look at that yellow interval, right? If you look at that yellow interval and you estimate from that yellow interval, if you estimate how much distance can you travel if you're traveling at the 85th percentile speed, there is a location that sort of becomes your, what we call the dilemma zone, right? So if you think about this, the idea is that if you are very far from the signal and you see the light turning yellow, right? They observe that most drivers from that point stop, right? But there comes a point where that percentage of the drivers that actually decide to stop, and then the percentage of drivers that decide to actually just go on yellow, maybe pedal or just sort of put a gas, put the gas on and just go, becomes higher at that point. So this is what we call the dilemma zone. And we'll work out a problem on the dilemma zone as well. But the idea is it's the zone at which you start to see some drivers deciding to stop and some drivers deciding to go. And that could happen to the extent any location, but there are specific thresholds at which we start to see almost everybody goes from here. Where if they're close to the stop line, up until a certain distance, everybody just goes. And then beyond a certain distance, everybody just stops. But in the middle, maybe it's the zone where maybe, so if you're here, if you're very close to this line, this first line, maybe instead of 100% being able to go, 70% will be able to go and 30% will decide to stop. In the middle, maybe it's 50-50. And go back here, it's 70-30 in the opposite direction, means 70% start to stop, 30% wants to go. And that's what causes, what we talked about is sometimes signals will make rear end crash problem worse. And this is the phenomenon that causes it, right? Because there is dilemma zone where some drivers will say, yeah, I could probably accelerate and just go. Some drivers will say, okay, no, I need to stop. And that's what causes problems. Yes, please.
With actuated signals, can't they implement something called the advanced yellow light dilemma zone that detects whenever or about the time when the signal is going to end, just to put on the yellow phase when it detects no vehicles are in the dilemma zone?
Yeah, so that's again, so those are sort of actuated, but these are not sort of technologies that you'll find at every signal. I think most signals will have that yellow signal to be basically specifically timed for each phase. So most locations won't have that, but there are some newer technologies where the light won't turn yellow until there are no vehicles in that dilemma zone that has been identified for that location. But there is actually a little bit of a downside to that based on how people behave, right? If you do that, then your dilemma zone will become, sort of start to become a little bit large in nature. Like, people will start to say, okay, the light, if I get close to an intersection, the light doesn't actually turn green. So as you would basically, by implementing those technologies, sometimes you encourage behavior that leads to higher approach speeds and intersections. Because drivers always would want to go, and then they might already do that, but they would want to get, if they know, or if they come to learn that the light never turns yellow when they're close enough to an intersection, they see a light green, they will speed to make sure that by the time light turns, or at starting to think about turning yellow, because the adaptive lights can think, right? So when the light's starting to think about turning yellow, they've already close to that point. And that could create problems as well. So yeah, so technology can help here by minimizing the dilemma zone to a lot of extent. But then again, it could cause some problems of sort of increasing the approach speeds as well, which may not be ideal. But you're right, those technologies do exist to sort of minimize the dilemma zone. So let's talk about, I shouldn't have numbered this. So just kind of some quick questions. What's the purpose of having yellow change interval as a component of traffic signal timing? To clear the intersection of vehicles, to reduce the likelihood of right angle crashes at intersection, the right of way, to inform the drivers that the right of way is about to end and they should stop, to allow the driver safely cross intersection if they're closed, if they're unable to stop before the signal turns red. So what is the reason, or all of the above? What do you think? Any thoughts? If you see more than one answer to be correct, you can say, you can guess probably. So actually this answer is all of the above. So this is sort of some of the explanations here. And yellow change interval warn the drivers that to safely stop at the intersection right away, or to let them safely cross if they're unable to stop, right? So so yellow light, if you see a yellow light, this is the time to make a decision where you're thinking, okay, should I just start to cross? Should I make my maneuver in a way that I can cross, or should I start to apply brakes at this point? And that depends on the distance there. And again, that leads to what we call the dilemma zone. And then also B is correct as well. Clearing the intersection by shifting the right of way. The yellow change interval reduces the likelihood of both right angle and head-on crashes, depending upon the phase sequence. So if you have sort of left-turning vehicles or crossing vehicles coming in, there will be fewer crashes of that type. Obviously, if you have east-west, right after east-west, north-south goes, then you're talking about right-angle collisions. If you're talking, otherwise, you're talking sort of head-on crashes between the left turners and the through vehicles, if the ordering of the phase is such. Yellow principle should warn the drivers. So this is sort of the principal purpose. If you're asked the principal purpose, that would be to let the drivers know that signal is about to change. And I know a lot of countries actually use, not the US obviously, but a lot of countries will use yellow at the start of green signal as well. But having driven in the US for such a long time, I find that confusing now. But there are countries that use yellow at the start of green phase as well. So that, they might find, the situation here confusing. It just depends on what you're used to. And then principal purpose, again, another principle for drivers that their right of way is about to end. So basically, change is about to happen. So all of these are sort of correct answers. Correct statement, yellow change interval at a signalized intersection. Which one you think is most correct statement here? So let's give it like maybe one read, maybe talk to your neighbor and see if you can figure this out. Maybe take a minute to read through this. Talk to your neighbor, maybe. Thoughts, questions? Does your neighbor agree with you? Think about that. Maybe neighbors. The purpose of the yellow interval is to clear both the vehicles and the pedestrian from intersections. Does that sound right? No, right? That's not correct, because that's all right interval is for that. So the A is not the right answer. Yellow change interval is unnecessary application at an intersection where a red clears interval is used. No, because the principal purpose, as we saw, is to let the drivers know that the right of way is about to change, right? So that's sort of a transition phase. So B is not correct either. Yellow change interval can be used to minimize the dilemma zone. Could potentially be done, like we could potentially do that. And then the last one is duration of the yellow change or red clearance interval are inversely related. The longer the yellow, the shorter the red interval. I don't know about this. I think C is probably the right answer here. Is that the current IT recommended practice, yellow and green interval are considered separately and calculated with different equations. So we don't actually worry about this stuff at all. When you're calculating yellow, that's an independent calculation than calculating the all red. So dilemma zone, the area upstream of signal where drivers face difficulty deciding. So if you properly time your yellow interval, you can reduce, you won't be able to eliminate it, because there would always be some distance where some drivers will have one decision and the others will have the other decision. So there's but you can minimize it if you increase the yellow interval, you could potentially minimize the dilemma zone. Okay. Incorrect statement now. So what we're trying to do here is which one is not correct. Which one is the incorrect statement? Talk to your neighbor potentially. Questions, thoughts? Does A sound like the correct answer? A sounds like it should be true, right? Or what do you think? How about A? Let's kind of go over these statements one by one. How about A? A seems like, yeah, if you make it too short or too long, that would probably make it unsafe. If you make it too long, you're basically asking drivers to kind of speed through it. And then obviously too short means that the dilemma zone would be longer there. The yellow change interval is intended to warn drivers approaching a signalized intersection to prepare to stop, not to proceed and clear the intersection. Yeah, I think that's fine, right? Like, you're warning the drivers but you could actually use that as a warning to, okay, yeah, you should go as well, right? So B seems like it could potentially be not correct. Let's see. C is the duration of the yellow change interval does not depend on vehicle classification. Rather, it depends on driver's perception reaction time. We saw the formula. It looked like, it does depend on perception reaction time. But if you look at the formula, there is that acceleration A in there as well, right? So if you have semi-trailer, maybe they will have a different deceleration rate than breakage rate. So it does seem to depend at least somewhat on. So C could potentially be wrong as well. So B and C is what I'm thinking right now. D is the yellow change interval and isolation. Yellow change interval at an isolated intersection should be longer than the yellow change interval at a coordinated signal. This one actually is true because at an isolated intersection, drivers might need more time to react to the change. Okay, so you want to give them that time. So I think A and D would definitely look correct to me. I'm not sure about B and C. Let's look at what's going on here. So B is correct, right? So the statement is correct for a jurisdiction where prohibitive yellow law. Okay, so this is something interesting here as well, because there are different types of intersection, right? There are different types of intersection laws that exist. And that's why I was trying to remember the idea of this question is think about this. I don't think California is one of those states, unless I've been driving wrong all my life, or not all, but at least last 15 years of my life. But I think California is not one of those states where you cannot enter the intersection on yellow. You can enter on yellow. But there are jurisdictions in the country where you are supposed to, if you are a yellow, you cannot enter the intersection on yellow. Once the light turns red, you're supposed to stop. Okay, so this correct the statement D would be correct in jurisdictions where, where the so it would only be correct. So I should put it, this would only be correct in locations where you cannot enter the intersection on yellow, right? Because if you can enter the intersection, it could be a warning to both, right? It could be warning to either clear the intersection, through the intersection, just go and not stop. But in some other cases, it might be a warning too. And the problem is, yes, you are basically taking away the dilemma zone, but then you might also be, if you're not allowing drivers to enter the intersection at yellow, you might be creating potentially unsafe intersection. drivers that are too close, right? So, but those types of things exist. So B would be correct in the situation where, so I would say the C is the incorrect answer because C depends. I think it depends on both, because if there is a lot of vehicles that are tractor trailer, then you might have to adjust your dilemma zone or your yellow interval, depending upon what kind of deceleration rate on average a vehicle can generate. So you might have to lower that number A if you have a lot of tractor trailers in there in your traffic mix. So and so we got this. Okay. Oh, am I going up? Okay, I need to go down. Sorry. Oh, we're almost out of time. Okay. So we talked about this problem. Yeah, I don't know why I'd say answer for B, but I think I should have said, if you look at the formula, you will see that that might not be the correct answer. Okay. So we'll talk about this last one, and then we'll talk about some other problems as well in the next class. Actually, not in the next class. In the next class, we have the test. And on the test, you're allowed to bring in one letter size page. You can write whatever you want front and back on it. Okay. And I will, and you can also use your warrant handout. Okay. Yeah, that's your next Tuesdays when you have the test. Oh, sorry, no. Next class is Thursday. Next class, we have the guest speaker, and we are going to do the review. And then 1 week from today is the test, okay? All right, sorry about that. So yeah, 1 week from today is the test. You are allowed to bring in one letter size page, whatever you want to write on it, that's fine. And then you're also allowed, and you should be bringing with you the traffic signal warrants handout. I will not be providing it. And if you have something written on it, I'm fine with that, right? So one letter size page and traffic signal warrant. I won't be checking what else you have on it, but you're supposed to, you can have the traffic signal warrant handout as well. Okay. All right. Thank you so much. I will see you Thursday.